Hello, we are still talking about regression, and in particular we're going to be still talking about the right-hand side of the regression. So regressions have a left-hand side, the thing that you are predicting, and a right-hand side, all of the predictors. And we've talked about some different kinds of things that might pop up on the right-hand side, like some transformations to your variables, some nonlinear stuff. Now for something that's going to pop up quite a bit and that you're going to see all the time, and that is binary predictors or categorical. A lot of the time, you have a lot of different kinds of variables, right? We talked about different kinds of variables in a video long ago, but one thing that pops up a lot is something that fits into different categories. Maybe it's something that is or is not. Did you get the treatment or not? That is a binary distinction, right? You can't really have half gotten the treatment. That doesn't really work. Or like, which continent are you currently in? There's only 7 options and they are mutually exclusive. You can't really be in 2 continents at once, outside of maybe like straddling the border or something weird like that. So we have a lot of predictors that we might be interested in that are binary in nature, or perhaps categorical in nature. And so what can we do if we want to include those on the right-hand side of our model, either as the variable we're interested in, maybe that's the treatment of some kind, or as a control variable. We want to control for what continent you live in. Well, it turns out to be relatively straightforward, and the key is this. When you include a binary predictor in a model, what it is doing for you is it is comparing means. That's what it does. So for example, if I, let's say, regressed your income on whether you got the treatment or not, and I got a coefficient of, let's say, 5,000 on the treatment variable right there. What that is saying is that the mean income is 5,000 higher for the group that got the treatment relative to the group that did not. It is a comparison of means. Exactly the same kind of comparison of means as you might do with like a 2-sample t-test, if you remember that from your statistics class. And so that is what we are doing with binary predictors. They are simply comparing the means across the yes of whatever your binary variable is against the no. Did you get the treatment? Yes or no? The coefficient on the treatment variable will give you the difference in means for the outcome between yes and no. And you can also add control variables like this. That would be a reason why you might want to do this over just a regular old t-test, for example. If you add control variables, you could then say controlling for all the stuff that I need to control for to identify my effect. The effect of the treatment on the outcome is coefficient, right? In which we can interpret as the mean of the outcome increases by this much when we go from 0 to 1. You can see why this might be for a binary variable, because let's go back to our interpretation of a regression coefficient. If I regress y on x, and then the coefficient on x can be interpreted as a 1-unit increase in x is associated with a coefficient-sized unit change in y. Great. Now, what if x is binary? Well, in that case, we're still talking about the exact same thing. A 1-unit change in this variable is associated with a coefficient-sized unit change in that variable. But if it's binary, there's really only a single 1-unit change that makes any sense at all. Going from 0, no, you're not in the group, to 1, yes, you are in the group, right? That's the only 1-unit change that you could possibly have. And so when we're talking about a 1-unit change, we're talking about going from a no to a yes. And so the coefficient gives you the jump in the outcome that you would see on average when you go from a no to a yes. And that's how we can interpret a binary predictor in a regression model. And as a bonus, we of course get a standard error and a significance test on that coefficient on the binary predictor, which allows us to see whether the average outcome is different, statistically different, between the group that is yes and the group that is no for this binary predictor. We can see that in action if we look at an example of an ordinary least square. So here's, I've got some basic data. So here I'm regressing your sales on whether it is currently winter or not. And let's say that your sales on average happen to be 10 when it's winter and 15 when it is not winter. All right. So in that case, what would happen if we did an ordinary least squares regression of sales on the binary predictor of whether it is currently winter or not? Well, I would get a coefficient of -5 on winter because the average the average sales in winter is 5 lower than it is in not winter. I would also, for the intercept, get a coefficient of 15 because that is the average for not winter. Right? If I'm getting a prediction from my model, it should give me the best prediction it possibly can, which is going to predict the average of winter for winter and the average of not winter for not winter. Where's my prediction for not winter come from? Well, I set winter to 0, and the only thing left over is the intercept, so that intercept must tell me what the average for not winter is. And then the coefficient gives me the difference between winter and not winter. It gives me the coefficient on winter relative to this reference group of not winter. The binary coefficient is always going to be a coefficient about being relative to something else, right? Winter versus not winter. And I bring that up and I emphasize that in particular because that is going to help us in the bridge to not just talking about binary variables, but talking about categorical variables with any number of categories, not just yes and no, in or out. So when we have a categorical variable, let's say we're going with continents or something like that, and we want to regress some outcome on this categorical variable, it's a very easy process. All we have to do is take each of the categories and turn it into its own binary indicator. So again, we're talking about continents. I would have a single variable for Asia. Are you in Asia? Yes or no. Are you in Europe? Yes or no. Are you in South America? Yes or no, and so on, right? Each continent would get its own binary indicator for being in that category. You might have also heard the term for binary indicators of dummies. I don't tend to use that one because if you're talking to somebody who doesn't know econometrics at all, and you're like, hey, I put the female dummy in the model, that might not go over particularly well. So I stick to binary indicator as maybe a better term. So we have the 7 continents, we have these 7 binary indicators, and then when we run the regression, when we regress something on those binary indicators, we have to leave one out. The reason why we have to leave one out is sort of a statistical reason. You can look in the book for the full explanation, but basically we do have to leave one out. And whichever one we leave out becomes what is called our reference group. And just like with the winter-non-winter thing, the coefficient on winter told us how much different winter was than non-winter, winter being that reference group. Here, whichever reference group we leave out, all of the other coefficients are going to be relative to that reference group. So if I leave out Asia from my model, for example, that all people in Asia are still in my data, they just don't get their own coefficient. They basically become the intercept, and everything else becomes relative to that group. And so the coefficient on Europe would not be like, what's the effect of being in Europe? It would be, what is the difference in means between being in Europe and being in Asia? It's always going to be that comparison. So not just is the coefficient on Europe going to be Europe versus Asia, but the coefficient on South America will be South America versus Asia. The coefficient on Africa will be Africa versus Asia, and so on. Everything is relative to that same reference group. Because of this, by the way, each of the individual coefficients don't really mean that much by themselves. They only mean something relative to the reference group that you have selected. Let's see an example. So here I've made up some data with some countries, and I've got income regressed on country. And I only happen to have 3 countries in my data: France, Gambia, and New Zealand. What a combination there. And the average income in France is 30, the average in Gambia is 30.5, and the average in New Zealand is 33. Now, if I run a regression, if I regress income on these sets of binary indicators for France, Gambia, and New Zealand, first of all, I have to choose one to be the reference group. I'm going to choose France just as an example. And then all the coefficients on the other ones become whatever the difference is relative to that emitted group. So Gambia had an income of 30.5, which is 0.5 higher than France's income. And so the coefficient for Gambia becomes 0.5. New Zealand had an income of 33, which is 3 higher than France. And so the coefficient for New Zealand becomes 3. And the coefficient for the intercept is 30, which is France's average income. It is our prediction when we set the Gambia and New Zealand variables to 0. And if those are both 0, that must mean we're in France. So France gets that intercept, so the average is 30, and everything else is relative to France. This also means, by the way, as I mentioned, those coefficients don't mean much by themselves. They only mean something relative to the reference group. All the coefficients would completely change if we happened to arbitrarily pick a different reference group. So imagine for a second that, let's say, I picked Gambia as the reference group instead. Well, now France would come back, get its own term in the model again, and it would get a coefficient relative to Gambia. So it would get a minus 0.5. New Zealand is now no longer being compared to France, it is being compared to Gambia. It's only 2.5 higher than Gambia, and so its coefficient would become 2.5. So all the coefficients, and therefore all the statistical significance tests, are completely arbitrary, and they're only based on whichever reference group you happen to choose. Which means that if you're interested in trying to do some sort of significance test on these coefficients, you have to make sure that you're doing a test that you are actually interested in. If I want to look at the coefficient for Gambia, and say, okay, Gambia is statistically significant or not, it is statistically significant or not compared to France. Is the difference to France significant or not? If that's not the question that I want to answer, I need to pick a different reference group. And I can't just look at the effect of Gambia all on its own, because you have to think about it, what it is relative to something else. If you do want to look at the effect of country overall and see if that is a decent predictor of income, you could do what's called a joint F test on these indicators, which is to do a test that looks at the joint significance of all the coefficients at once. Your null hypothesis is that all the country coefficients are 0, and so everything is not at all different from France, right? Everything is exactly the same as the reference group France. And if we can reject that or not, we can do an F test to find out. All right, so that is how we can incorporate binary predictors into our regression models, and of course how we can also incorporate categorical predictors by just turning them into a bunch of binary predictors. This is something that's going to come in handy quite a lot because it comes up very often in actual analysis. And I'm sure that once you start doing your own projects, you will see that. Thank you.